You can accomplish the dehydration of alcohols when there's a hydrogen on the adjacent carbon to make an alkene. Now you'll notice that this requires that OH be a leaving group if this actually happens in one step. And we know OH is a very poor leaving group, so that doesn't happen. But rather the OH is converted into a good leaving group, and then dehydration occurs readily. The classic way for converting this into a good leaving group for dehydration is to use a very strong acid. Concentrated sulfuric acid is classical. Now I'm going to put concentrated above it because that is very important. It's important because, well, do you remember this? Alkenes are converted by treating with sulfuric acid and water to make alcohols. So, putting these two together, we see that what we're saying is this is a reversible reaction. And the fact that water is a byproduct in this reaction is very important, because now it becomes clear that this right side of the equation is the same as the right side of the equation here if we write H2O plus alkene rather than putting it down below the arrow. So these are different directions of the same reaction, a reaction that's reversible. And the things that we knew about this reaction, initial protonation, addition of a nucleophile, loss of a proton, are the same steps in reverse order that account for dehydration. Take a look. Reaction mechanism involves initial protonation by sulfuric acid, where we picture a pair of electrons from the alcohol oxygen accepting a proton from sulfuric acid, and this pair of electrons stays with the oxygen. So the first step of this reaction turns the hydroxyl group, a lousy leaving group, into water, a very good leaving group. And then in a second step, also reversible, the water leaves to make a carbocation plus water. And ultimately then, in a final step, the proton from the adjacent carbon is lost to a base. I'm going to ask you something about this in just a minute. As the base takes the proton away, the electrons from that sigma bond are available to form the pi bond. And here's an alkene. Let's talk about this a little bit. First of all, the base. What's up with that? We're in very strong acid and we're talking about a base? Well, this wouldn't be a basic base. This would be something that accepts a proton. And there are two candidates. There is a water molecule. So the water molecule is a possible candidate for accepting that proton because it has pairs of electrons. The other candidate for base, and this also happens, is the bisulfate. The conjugate base of sulfuric acid that we generated in the first step when it did this protonation. And perhaps not to avoid being sneaky, we should say plus. So this base is not a strong base, but this carbocation is a very strong acid. And it will protonate water, and it will protonate bisulfate to make sulfuric acid. When sulfuric acid is protonated, it's clear that that regenerates sulfuric acid. Sulfuric acid is a catalyst. Now, there are two or three things to say. Number one is, notice that this is an E1 mechanism. And we know that E1 mechanisms are typical of tertiary and secondary substrates. Primary alcohols also undergo dehydration. We're going to have to modify our scheme here to accommodate the E2 mechanism for primary substrates. Number 2 is that in terms of rates, like a normal E1, the tertiary is faster than secondary. And another thing to notice is, like other carbocations, that carbocation intermediate may rearrange. So there's definitely some drawbacks, like rearrangement, from using this acid-catalyzed dehydration of alcohols, but it's a very effective reaction. It's used extensively for at least the dehydration of simple alcohols. Now we've mentioned that this is a reversible reaction. Each one of these steps is drawn as an equilibrium step. Here's the overall equilibrium shown. But the question is, which direction is favored? Well, we learned that the addition of water to alkenes is done using dilute sulfuric acid. So addition of water shifts this equilibrium to form the alcohol. And by the same token, removal of water shifts this equilibrium to favor product, the alkene. And that's where this concentrated sulfuric acid comes in. Concentrated sulfuric acid removes water, forming the hydronium ion, which no longer is a nucleophile to go backwards. So one of the ways that this reaction is run to favor formation of alkene, dehydration of alcohols, is to remove water using concentrated sulfuric acid. It's also possible to remove water other ways, such as distillation, or using compounds called molecular sieves that selectively absorb water. But in addition, it's worth noting that these reactions are carried out with heat, sometimes even high heat. And why would that be? Well, the overall equilibrium term is described by the equation for free energy, and adding heat to this reaction increases the importance of the entropy term. Now you recall that when the change in entropy is positive, meaning more disorder, we are multiplying two positive numbers, temperature and entropy, which means this term itself is negative and increases the negative value of delta G. Negative values are good, favor products. So increasing the temperature increases the importance of the change in entropy. Now, does that favor products? Well, yes, it does, because in the initial starting material, everything is tied together and more ordered. And in the product, we've separated the alkene from the water, and those are free to go their separate ways, created greater disorder. So heating accomplishes two things. One, it provides energy for the reaction to happen, so we can surmount the activation energy barrier. And secondly, it makes the entropy term important when entropy actually favors formation of product. So bottom line is, in a reversible reaction, it can be described typically as an E1 reaction. Alcohols are dehydrated using concentrated sulfuric acid and heat in reasonable yields. A couple of other side notes. One is, of course, when it's possible, both E and C isomers will be formed. There's no stereochemical control over this because we're looking at a carbocation intermediate. Any stereochemistry that exists in the starting material is lost after the alcohol departs. So E and C isomers prevail, and typically the E is favored. And finally, let's remember that the primary alcohols dehydrate by the E2 reaction, not E1, after the hydroxyl group has been protonated to form a good leaving group in an initial equilibrium step, accepting a proton from sulfuric acid and then losing a proton to base, which would be water or bisulfate, the bisulfate being formed in this initial equilibrium step. So we have an alkene. There's 2 hydrogens on that carbon. And just to tie up using arrow pushing to detail the mechanism, pair of electrons on that oxygen, pair of electrons on that base. Protonation of the hydroxyl group. The electrons stay with this oxygen. Loss of this proton to base as this pair of electrons forms the pi bond and this water leaves. Remember, in the E2 reaction, everything happens at once to form alkene and protonated base. So there you have it. Dehydration of alcohols uses concentrated sulfuric acid and heat. The equilibrium favors the formation of the alkene, and it occurs by an E1 reaction for secondary and tertiary alcohols and an E2 mechanism for primary alcohols. Very useful in organic synthesis when there are no other functional groups in the molecule that will be affected by the strong sulfuric acid.